Welcome to a lesson with Dr. Powell. Let's take a look at an example where we determine if a critical point which is given represents a maximum, a minimum, or neither of a function. Okay, so look at its first derivative by taking partial derivatives with respect to one variable at a time. So the first one is, this is fx, fy, and this is fz over here. Okay, so with respect to x, we think, okay, that's 4x. Here, y is like constant, so like 2y times x, so it's 2y. Here, that's a constant, it's gone. Here, it's just z is the constant multiple of x, is just z. That's a constant, that's gone. Cosine of x derivative is negative sine. All right, then we move to fy. So with respect to y, we get 2x as the constant multiplier of y. Then we have plus 2y. Okay, and everything else are like constants, they go away. Now x plus 4z, let's see how we got that. So take a derivative with respect to z, that's like a constant, gone. Here, the constant multiplier is x, and then here we get then we get just derivative of this is 4z. Great, so that's the first derivative as a matrix. Second derivative, how do we do that? Well, we take this and think of it as a column and take partials. In other words, we just go down this list and take partials with respect to x and put our results first column. With respect to y, second column. With respect to z, third column. So let's do this first. So let's go down here with respect to x to get the first column. With respect to x here, we get minus cosine x plus 4. Okay, that's the first guy. Then we look over here, we get a 2. Okay, over here, we get a 1. All right, now we go down this list for y's to get that. So for y's, we get 2. Everything else is constant. Okay, over here, we get 2. And then here, that's just a constant, so 0. Then we do it for z's. We go down through here, we see a 1, right? Everything else is like a constant. This guy, that's a constant, so 0. And this guy is just a 4. We just found the second derivative. Notice that it's a function of x, all right? But we have a critical point, so we need to plug in 0, 0, 0, and we do so, and we get this matrix right here. So this is the matrix we're going to consider. We know we have a critical point, 0, 0, 0, meaning that the first derivative will be 0 there. You can check it to make sure, but it's pretty clear. If you plug that in, you get zeros, sine of 0, 0, 0, 0. Okay, so that's a critical point. This is the second derivative. Now, let's decide what the second derivative will tell us. All right. All right, so we're going to let x represent the matrix. Oftentimes people use maybe another letter, lambda, not to confuse the variable with an x that's already being used up here. But we'll remember that they're distinct and they're different. Okay, so this x in this case now represents the matrix itself. Okay, now the matrix after we've actually plugged in our point, right? So we don't want to do this process with variables in here and stuff. We want to have just numbers, right? So that means we want to plug in our critical point first. Remember, first plug in your critical point, then you get this matrix, then you can represent it as a new variable x. Then we can think about a characteristic polynomial by taking a determinant. Now, in this particular case, I actually expand along this column. So -1 times the derivative, what's kitty corner to it, right here. And we end up getting x minus 2. We don't need to change the sign of this location because we have plus minus plus over here, or this one too, plus minus plus. So we have that times that, and x minus 4 times this, which we can get by this determinant here. And we multiply that out, we get this, and then multiply it out again, we get this. We can use Descartes' rule of signs. Notice we have 1, 2, 3 sign changes. So that means that for positives, we have either, by Descartes' rule of signs, we have either 3 or 1. So we're not quite done. We got to look at the negatives. So at the negatives, with Descartes' rule of signs, what we do is we plug in a negative x in for x here, everywhere, and see what happens. If we plug a negative x in, we get a negative x cubed. This stays the same, negative 9x squared. Negative x, that changes that sign, negative 21x and minus 6. Any sign changes? No, which means that there are 0 possible negative roots, but all of them have to be real because it's a symmetric matrix. Therefore, there's exactly 3. So all of the roots are positive. All the eigenvalues are positive. So what does that mean? That means that at this critical point, we have a minimum. So it's not too hard to determine if something's a minimum or maximum. If we can remember this is a symmetric matrix, we can use Descartes' rule of signs, and all we need to do is just compute what the characteristic polynomial is. Thanks for watching.